Hi students. So today we are going to start lecture 55 in our aerospace engineering course, and today I'm going to discuss about static longitudinal control. We also sometimes refer to this whole lecture as stick fixed stability. So we are going to look at some of these aspects. Until now we have been looking only at pure stability. Now we are going to look at how we can control the pitch motion of the aircraft. I'm Dr. Anjan Ganguly. Now let's go back to the line we started with, and that was the line for CMCG with respect to alpha A. So just recall that if the aircraft is flying, it's flying at some angle alpha E, and then CMCG is 0. This condition is known as trim. So this particular trim or equilibrium condition of the aircraft is the point where this red line intersects with this axis here. So this is the point where CMCG equal to 0, alpha equals to alpha E, and this is known as the trim or equilibrium condition of the aircraft. Again, recall that the slope of this line is given by dCMCG by d alpha A. Now, we are going to be faced with certain problems. Suppose we have trimmed the aircraft and we are flying in a realistic situation. So when you have the aircraft in the trim condition, alpha A equals alpha E, which means you are effectively flying at this point here where this line is meeting the axis here. Now at this point alpha E corresponds to some value of CL, which is CL trim, and you can easily obtain these values or the relation between the velocity and CL trim given by this equation here. So remember, we are in steady level flight, so the lift is equal to the weight, and therefore I can easily obtain this relation from the definition of the lift itself, that is lift is half rho v square into S into CL. So from that equation we obtain V trim. So essentially what this means is that when the aircraft is in the trimmed condition, V trim will be given by this formula. Now what happens is that there may be a situation where the pilot wants to change the velocity slightly. So he may want to actually create a situation where V infinity is less than V trim, and in that case what he will have to do, he will have to increase alpha, so alpha A become greater than the equilibrium value. So again alpha has to become greater because the velocity is lesser, and so more of this angle is required to drive the CL value up. Now in this case, if we look at this graph here, we will see that in the alpha A greater than alpha E region, which is this green part of the line here, CMCG is less than 0. Therefore what's going to happen is that the aircraft is no longer trimmed here, and so you have a situation where in this green line here alpha A is not equal to alpha E, and so the trimmed condition has been lost because the pilot wanted to actually bring the velocity to lower than the trim velocity. Now in the current slide we are going to discuss the reverse case. So again you are in the trimmed condition, so you have alpha A equals alpha E. Your situation in trim is such that you are flying at this CL trim value. The V trim value is given by this equation here. Now what happens is the pilot wants to increase the speed, so V infinity should be greater than V trim. Now in this case the alpha A value has to be decreased from the equilibrium value alpha E, because what's happened now is that you do not need to create so much lift from that velocity itself, because the velocity has gone up, so therefore the CL value can be less, so therefore alpha can be less. Now in this situation we are actually on this part of the curve, which is alpha A corresponds to alpha A is less than alpha E, that's the green part of the curve, and here you can see clearly that the situation will be such that the moment CMCG is going to be greater than 0. So once again you do not have a trimmed situation and you have essentially lost trim of the aircraft. So essentially whenever the pilot is trying to fly faster than the trimmed velocity or fly slower than the trimmed velocity, he is going to essentially lose the trimmed condition, and there must be some mechanism by which he can retrim the aircraft. So we are going to look at that next. So the question is how to retrim the aircraft. So one method which could come to your mind is that if my green line here is the first condition and essentially I have lost the trim condition, it has come to alpha n, I could simply move this line to this blue line here. So this would entail that I am changing the slope of this curve. So in this case the green line becomes the blue line. Therefore the derivative of CMCG with respect to alpha A, which was in green here, is changed slightly and it becomes this line here given in blue. So this concept of changing the slope is of course theoretically possible, and we can go back to our previous lecture and see that this slope is related directly to A into H minus Hn, which is also the distance between the CG and the neutral point. So theoretically, since the neutral point is fixed, you could move around the CG and you could change the slope of this line by moving around the center of gravity of the aircraft. Now this is of course difficult to do in a realistic aircraft type of situation, but this method is used in certain flight vehicle type of systems such as hang gliders. You could probably think of some drone conditions where this kind of thing could also be possible, but it's impractical to do for typical conventional airplanes. So what is a more realistic method would be to actually shift this line in this method, that is change the CM0 value, and this can be done by using the elevator, which is the control surface which is put on the horizontal tail. So essentially the idea here would be that you would have this green line here. This is a trimmed condition. You want to move this line to a new line here, the red line here, where the trimmed condition is given by alpha n. And so what you could do is that you could change the CM0 value and you could keep the slope of these two lines exactly the same. So that's what you see here. The slope of the line is the same, but the CM0 value has changed. So let's see how this can be done. So to start with, consider the typical tail section. Remember, tail sections are typically symmetric. You have a velocity of air coming at v dash, and you also have this angle alpha subscript t, which is the angle which is seen by the tail. This angle is relative to the zero lift line for the tail. Now what I have shown here in blue is the elevator when it is not deflected. So essentially it is at zero deflection. So in this kind of case, the CLT versus alpha t plot would be the typical lift curve here. And because we are considering the zero lift line, of course, it goes through the 0 point, because that's the way we have actually defined alpha t with respect to the zero lift line. So remember, this is the absolute angle of attack for the tail. So now if we were to deflect this elevator control surface, what would happen is that this deflection would be given by this value delta subscript E, and then we can get several different curves depending on the value of delta E. So again, think back about the trailing edge flap type of situation. I have made a video long ago in this lecture series on that. So what would happen is that as the delta E value goes up, say from 0 to 5 degrees, from 5 degrees to 10 degree, new curves are obtained. So here I have the curve in red, the curve in blue, the curve in green corresponding to 0, 5 and 10 degree. So in these curves the slope is same, but the CLT value is obviously changing. So it is typically increasing as the delta value goes up. So now one of the things to remember of course here is that the elevator deflection is positive downward. So you can see in all these cases the deflection of 5 degree or 10 degree means that it's a downward deflection. So if we were to fix the tail at some value, let us say some value alpha t1, then what would happen is this line would correspond to this fixed value, and you can see here in this case that only the delta E would have an impact on the CLT here. So essentially at a general point, I would say CLT would be a function of both alpha t and delta E. So if you were to freeze any of these values, you would get to vary the remaining values. So this essentially lets us immediately write some equations. So we can write CLT is a function of alpha t and delta E, where alpha t is the angle seen by the tail and delta E is the elevator angle. Now, if we were to plot CLT with respect to delta E, we typically get a line like this, and the line like this is such that it goes up. So CLT by delta, or rather dCLT by d delta E is a positive value. So essentially it goes something like this. So this is what we have seen in the graph before, and based on that the line like this can be drawn. Now we can immediately write CLT in this form from calculus chain rule. So it's the derivative of CLT with respect to alpha t into alpha t, and the derivative of CLT with respect to delta E into delta E. So you recall this from basic calculus, is that if there is a function which is a function of these two variables, so for example this could be x and y, then I can write it like this. So then I would try to simplify this expression further and figure out what is the trim control angle. So now let's do some math here. So CLT is given by this formula. I showed this in the previous lecture. Let's simplify it by calling this first partial derivative as AT. So it would simply become AT into alpha t. AT is the lift curve slope corresponding to the tail. Now go back to the CMCG formula which we have obtained in some of our previous lectures. So you know that CMCG is component due to CMAC at the wing body, then that is the component due to the wing body itself. CLWB is the lift coefficient of the wing body. The value H minus HAC is there, and then you have the component which is coming from the tail. So that's related to CLT. So now what we do is we take this CLT here, which I have shown in this yellow box, and we plug it into this equation here. So I get CMCG as this equation here. And now what we do is that we are going to simply differentiate CMCG with respect to delta E. So that's an easy derivative because all these terms are going to get zeroed out. And so I only get minus VH into dCLT by d delta E here. So that's the derivative. So you can easily see the derivative comes out in this manner. Now with this I can get the value delta CMG is minus VH into the derivative into delta E. So all I have done is I have taken this derivative here and I have written it in this form where I have assumed that these derivative values are slightly larger values. So in that case what happens, the top delta has become in this form and the delta E here has gone here as delta E. So this gives us the change in CMCG due to a deflection of the order delta E, and this is going to let us figure out how much delta E is required to change CMCG by a certain amount. So that's the essential question. What is the delta E needed to trim at alpha n? So this is the question we wanted. We were in this green line here. We wanted to come to this red line. And so a certain delta E value is required to get this alpha n. Now to do this mathematics, let us start with the fact that we consider the green line here. And this delta E equal to 0 line is y is mx plus c. That's the general line for a straight line or general equation for a straight line from any coordinate geometry book. So now we know m is the slope, so that's d cmcg by d alpha a, and also the intercept is given by cm0. So essentially the line here is given by cmcg equals cm0 plus d cmcg by d alpha a into alpha a. Now what I do is that I try to get the situation if there is a presence of this delta into this line. So in that case what happens, there is this delta CMCG term which is coming because the elevator deflection has happened. So this is the equation of the red line here. So now immediately I plug in the delta CMCG value obtained in the previous slide and I get this equation. So this equation for CMCG actually includes the effect of the elevator angle delta E. So this is the line given by delta E here. Now let's again write that equation out and then enforce the condition that in this line, if it was to be the line for trim, CMCG would be 0 at alpha a equals alpha n. So I can take this equation here, I can set it to 0. So that means CMCG is 0. And I set alpha A equals alpha n. So that's here. And I also set delta E equals to delta trim. So then this becomes exactly the line in red shown here, and I can now calculate the delta trim value. So if we simplify this equation, we can get delta trim is this equation, and this is the angle you need to give to the aircraft or to the tail elevator deflection such that you are trimming the aircraft at this alpha n value. So it obviously depends on alpha n, and there are some more parameters in this equation. So let us look at this equation very carefully because this equation talks back to you. So what happens here is that delta trim depends of course on CM0. It also depends on these two derivatives which are typically obtained from wind tunnel tests. So these are derivatives of CMCG and LT with respect to alpha A and delta E respectively. So you can get these results by making certain model specimen and testing them in wind tunnel. VH is typically known for the airplane because that's a parameter coming from the different aspects of the tail. So do recall in previous lectures we called it the tail ratio, and of course alpha n is the value you have at which you want to essentially trim the aircraft. So that's something you also know. So you essentially can calculate delta trim and trim the aircraft. So this was an important issue we discussed today. Now just to make certain points, what we discussed today is known as fixed stability. So essentially what happens here is that any pilot, this can be a human pilot or it could be just a control system if you are doing some kind of automatic control. What they would do is they would move the control stick so that the elevator angle is set at some value delta E and then simply hold this value at delta E. So this means that they rigidly hold the stick at this point and therefore the stick is supposed to be fixed. Now modern airplanes typically have hydraulically mounted power control. So using this kind of mechanism where you hold the stick and you fix the value at delta E is easy to do, and so this is known as stick fixed stability. You would essentially hold the delta value at this particular value we have derived today. Now in many old airplanes what happens is that the control stick is connected to the elevator via wire cables without any power boost. So in that case what the pilot has to do is that he has to continuously give a moment force to keep the stick fixed, and this is not a comfortable situation, it's highly impractical. So therefore this kind of stick fixed stability is not used in some old or ancient airplanes. So what happens instead is that the control stick in those situations is left to be free, and so what would happen is that the elevator is left to float under the different aerodynamic forces which act on it, and it is going to find its own equilibrium position. So this is known as stick free static stability. That's something which we are going to discuss in our next lecture. So just to recapitulate today's pretty important class, we saw that the tail by itself, it of course plays a big role in stability, but then you also have the elevator and that plays a role in terms of trim and control. So this can be used to trim the airplane in pitch. So there are two variables here. There is the alpha t, which is the angle seen by the tail, and then there is the delta e, which is the angle which the elevator has with respect to the zero lift line. And what we can do by that is that we can move this green line which corresponds to delta equal to 0 to this red line here, which is essentially the way we can trim the aircraft. So if we give this value delta trim, we can trim the aircraft to alpha n, and this is the way the pilot typically trims the aircraft in regular flight in terms of the pitching motion. So with this, we clearly have a good idea about the longitudinal static stability and also some aspects of longitudinal control. And so we know how important the horizontal tail is in terms of stability and the elevator is in terms of control and in bringing the aircraft to trim after any situation of change in velocity and so on. So in the next lecture, I'm going to look at the situation where we have stick free stability and control, and so that will probably finish the longitudinal stability and control part of this course, and then we are going to look at the directional stability and the lateral stability very briefly. So I'll end this lecture here. If you have any questions, please leave them in the comments below and I will try to answer them as soon as possible. See you soon.